All right, time to get started. Hi, I'm Drew Dahlke. I'm a software engineer at WhyLabs, and I'm here to talk today about migrating our ML Insights platform to Apache Druid. We recently migrated our platform from Elasticsearch to Druid, and I'm going to go do a little bit of a technical deep dive into what large-scale data ingestion looks like for us and what made Druid such a better fit for our platform. So I'm going to cover streaming and batch data ingestion. I'm going to deep dive on replication and how that affected our business. We have extended Druid pretty heavily, so I want to talk about some of the reasons why, and we'll also touch on performance, some best practices, and let's get started. So a little bit about what we do at WhyLabs. WhyLabs is a data and machine learning observability platform that monitors your data over time and alerts on issues that could affect your data quality and machine learning model accuracy. And so in the screenshot over here on the right, we have a data pipeline that we're watching, and we're tracking every feature in a particular data set. And then every time that data pipeline runs, which is once a day, it's producing a statistical fingerprint of what that data looks like. And we're able to do some time series anomaly detection and alert to issues that are going on with data in that pipeline. Now, we started with Elasticsearch, and Elasticsearch is fantastic as a search product, but you can kind of tell that this isn't really a search product. This is all about time series analysis, and we're now powered by Apache Druid. And if you've never experienced the responsiveness of a production Druid-powered application yourself, we actually have a free sandbox you can log into and click around. I'd invite you to do so. So I want to talk a little bit about where I see Druid fitting in the data ecosystem. On the far left, we have the analytical space, which we have a small number of people that are working with absolutely massive data sets. And your performance is kind of measured in query concurrency. So if you're using something like BigQuery, you probably have maximum 100 running queries per account level. Whereas on the OLTP space, that's more what powers most of the websites on the internet and easy to use by the general population. Many queries per millisecond query speeds, and the speed of data availability could be anywhere from instant to a second, just depending. And these are all really desirable aspects to have in a data tier. But the downside is it all falls apart once you start doing analytical queries with lots of scans against really large data sets. It gets astronomically expensive. So in the middle, this is where Druid really takes the crown, where it's taking some of the power of the analytical side, but stealing some of the performance aspects from the transactional side. To achieve that, they've got some, you kind of have to embrace some things like data is immutable once written. Uh, your data needs to be time series, things like that. But if your data fits within those constraints, then Druid could be a really good option for you. So I think it's really, I really like to compare Elasticsearch to Druid to make you appreciate Druid more. So I'm going to talk about what streaming data into Elasticsearch looks like, and then we'll compare Druid on the next slide. So here's a really common architecture I've seen at many companies where you have a shared tables, a couple microservices writing data to the tables. And one day, microservice A wants to ingest a whole lot of data. And it ends up being this huge song and dance to ingest data as fast as you can, but don't push too hard or you start hurting your cluster. And well, when you start doing that, microservice A can start affecting microservice B. And so now we're starting to ask questions like, well, should we be tuning our connection pools? Should we implement circuit breakers? Should we maybe merge those microservices or break it out into multiple Elasticsearch clusters so that they don't affect each other? These are all like really complex architectural questions that aren't really where I want to spend my cycles. And there's also issues like if microservice A is trying to write a record to Elasticsearch, and if it times out, there's no guarantee that it actually failed. If you're doing something as simple as incrementing a counter, and you get a timeout after 30 seconds, you're going to retry the timeout and potentially increment that counter. I think this is fine in the in a search engine. People don't necessarily expect if you go to Google and you search for puppies and you get different results every time you do that search. That's okay. In a form where you expect accurate answers and the same answer every time you run the query, it becomes less okay. So you end up having a lot of people do CRDT strategies, but it's a lot of complexity to your data modeling that I would also not like to have to think about. So let's talk about how Druid does it, because it's very different. With Druid, they couple the streaming ingestion tasks with the Druid cluster. And so instead of talking directly to a REST API, you're talking to a message broker, and the Druid either Kinesis top index task or the Kafka index task can perform exactly one stream consumption, and you don't have to worry about any fancy CRDT strategies or double counting. It's just managed as an exactly once consumer, which is fantastic. Also, each task is dedicated configurable resources. So I can say, hey, task A gets 2 CPU cores, task B gets 4 CPU cores, and task A really doesn't care how busy task B is, it's just not affected. But they're still able to share that overall Druid cluster. And then as far as, well, that song and dance that I used to do with Elasticsearch to try to adjust data as fast as I could, well, we've limited the client-side HTTP connection pool. We don't need any circuit breakers, and I don't need to be concerned with server-side HTTP thread pools getting overwhelmed. The data gets consumed out of the Kafka or Kinesis topic as fast as those 2 CPU cores can pull it down and ingest it. And that's maximum efficiency without all that um, thread pool and connection pool, without all that complexity. So one of the things that we get from Druid that most other data tiers don't offer is streaming merge on write. So a typical use case for us as a customer might be profiling a Kafka topic. They want to watch the data shape change over time as data is moving through that topic. And they might be in a distributed environment. Let's say they have 2 consumers on that Kafka topic, and they might be producing statistical profiles once an hour, all to produce a single daily data point once they push it into the cloud. They might only be interested in data. And so if we're ever to do a profile that gets sent to the cloud, that would have write amplification of about 48-fold more than it needs to be. Whereas in Druid, I could specify a query granularity of day, and Druid will maintain that in-memory buffer and merge that data as it's coming in the front door without me having to have a dedicated microservice to do something like that. And so that really helps with reducing our costs to deal with data volumes that we get from customers logging data in a horizontally distributed environment. So the next thing I want to pick on Elasticsearch for is replication issues, and we'll talk about Druid on the next slide. So let's say microservice A writes a document into Elasticsearch node 1, which has the primary shard. It gets a 200 back, and this is fine. But the replication can fail. The replication is asynchronous. And so now I can get different query results machine I'm getting load balanced between. And well, again, that's fine on a search product to have different search results depending on which day you run that query. And an analytical product, if I tell you that there's 2,000 unique values and then 100 unique values, and I'm fluctuating between those 2 numbers depending on which server is answering the question, well, in analytics, accuracy is king. And if your numbers are fluctuating, you lose that trust from your user. The other problem I have is what happens once able to scale up when you need it to scale up the most. Also, never dip below your replication quorum or it's data loss. So let's look at Druid. So with Druid, I've heard some people call it a bit of a Rube Goldberg machine, but once you start peeling back the layers, it makes a lot of sense. So the data nodes don't replicate directly to each other. If a node is ingesting data, those Druid smush files or Druid segments are being pushed to a distributed blob store, S3, HDFS, what have you. And then the other nodes are reading from that distributed blob store. And this is wonderful when I need to add a new node because I've maxed out the capacity on the hardware that I have, because the new node can hydrate from S3 and not have to stress already stressed machines. Makes it much faster and cleaner to scale up when I need it to happen fast. Also, when reading one of those Druid segment files, it will read the entire contents of the file before it registers that it is ready to service queries on that file. So you never have that Elasticsearch case of, oh, a single record failed to replicate you in the Druid world. Um, Also, losing replication quorum is self-healing because machines can come back online and hydrate that data from S3. I could actually take my data tier ASG and shrink it down to 0 and then back again like an accordion, and everything would self-heal, hydrating back from S3. I can't say that about very many other data tiers, and that's super cool. So when it comes to indexing performance, and of course we'll do Druid on the next slide, I'm not going to share any numbers because everybody's story is going to be very different. Instead, I want to focus on why is it so much faster to throw massive data volumes into Druid compared to Elasticsearch. And to do that, we need to talk a little bit about what is happening. So when you index a document into Elasticsearch, it's going to do some tokenization, some analysis. And what it's doing is it's trying to build an inverted index of, hey, here are all the terms in that document, and here are all the document IDs that have that term. And this makes for extremely performant point lookups, which is perfect for a search query. If somebody does a search query for a couple terms, we're able to get the list of documents that contain those terms because it's indexed. However, it's a very expensive way to index large amounts of big data. Elasticsearch is trading really expensive writes for extremely fast point lookups, which is what you want in a search engine. It's not what you want in an analytical product. So ingesting data into Druid doesn't do all these. We're not trying to build B trees. We're not trying to build inverted indices. Druid stores data bucketed by time range, by column, with columnar access to dimensions and metrics. And when a query comes in, it's going to use things like the query interval, which fields are being aggregated, partitioning information, and every trick in the book to try to reduce how much data they have to scan to fulfill that query. But at the end of the day, every query is a scan. It's just a very optimized scan. So if you're to benchmark Druid against Elasticsearch, you might find that, okay, Druid might not match Elasticsearch's queries per second on a point lookup because it's not maintaining indexes. But on the flip side, Elasticsearch cannot match Druid's queries per second on analytical queries that do scans. Druid's just built better for it. And when you look at the WhyLabs platform, most of the screens that you see are scan a range of time, aggregate, group by time series, render it. And that's the workload that we have in our product, which is a much better fit for Druid. So I want to talk a little bit about extending Druid. WhyLogs sets the standard for open source data logging, and we use a lot of probabilistic statistical algorithms to model the shape of data while preserving privacy. And we're talking hyperlog log, theta sketches. I'm going to kind of nerd out on one of those on the next slide in case you're not familiar with that. So hang in there with me. And what are we doing? So customers probably have JSON, some CSV, some Parquet, they might have some images, and they might be processing them with some Spark, maybe Pandas, maybe SageMaker, Flask, Kafka, you name it. You can use the WhyLogs data logger to produce statistical profiles. And some people stop there because the statistical profiles themselves are really useful just on their own. However, if you want to monitor them over time, visualize it, and get alerts when sudden shifts of patterns happen to your data, well, then grab an API key and start uploading that to the WhyLabs platform, and then you have access to visualizing all of that in the cloud. So we picked, one of the reasons why we picked Druid as our data tier is that they supported a good number of these algorithms out of the box. And we knew that for all the algorithms that we have in WhyLogs that we that there wasn't a data tier on the planet that supported all of the algorithms that we planned on using. But Druid supported enough of them that we knew that there was a lot of prior art, that we would have a good foundation, that we could kind of copy paste and start swapping out algorithms and kind of grow from there. And the last 6 months have been a whirlwind. We're already at 5 extensions and we're growing fast, adding new algorithms as we're adding them to WhyLabs. So let's nerd out about Hyperlog real quick. So here's a common scenario with our customers. They may be profiling a Kafka topic using the WhyLogs data logger, producing statistical profiles. And let's use this to answer a question. Let's ask how many unique email addresses on a particular feature on an event have flowed through this Kafka topic. So Hyperlog starts with a fixed size byte array. And as you're feeding data into a Hyperlog log, what you're really just doing is taking that these email addresses, we're gonna do a hash and mod it by 20 because I've got 20 bits. And if that bit is 0, we're gonna flip it to a 1. We'll add the rinse repeat. Here's my email address. Hash and mod by 20. Okay, let's flip that bit to 0. Now, after we've gone through this exercise, I can see I have 2 bits flipped, and I can infer that I have had at least 2 unique email addresses flow through. Now, we're going to get hash collisions, and that's expected, and the raw data here is discarded, so it's very privacy preserving. I can have multiple email addresses hashing and modding to the same single bit. And also, Hyperlog is a fixed size byte array, so it doesn't matter whether we're going over 1,000,000 rows or 1,000,000,000 rows, it's a fixed memory footprint, which makes profiling data very predictable in the amount of overhead required. Well, fun fact, WhyLogs and Apache Druid share the same Hyperlog implementation, which comes from the Apache Data Sketches library. The main difference there is that WhyLogs is taking this really cool algorithm that was usually only used in databases and kind of offering it outside of the database context. So let's kind of play this out. Let's use Hyperlog and compare what does it take to do a count distinct versus an approximate count distinct. Now, in the Druid world, if you wanted to do a count distinct and you had 3 terabytes of data, it kind of turns into a little bit of a classic MapReduce. You need to sort and shuffle 3 terabytes of data over the network in order to determine how many unique values that you actually have. The difference when you start doing Hyperlog distinct calculations is you no longer have to sort the data. You just groom over the entire chunk of data, build a Hyperlog, and then you can merge these 3 Hyperlog data sets together and produce a cardinality estimation that's 98.5% accurate. But the key here is that we're only having to shuffle 3 kilobytes of data over the network rather than having to do the entire raw data set. And so this is what makes Druid when doing an approximate count distinct. And WhyLogs is taking that same technique and offering that outside of a Druid context, outside of the database world. So when extending Druid, Hyperlog is but one of the many algorithms in the WhyLab toolkit. A lot of the algorithms that we use come from the Apache Data Sketch project, and Druid being written in Java meant that it was going to make it very easy to adopt more of the algorithms from the Apache Data Sketch library into Druid than what is available. And right now, kind of that flow is that our CI pipeline tarballs up our extension, and the Imply platform rolls out our extension to our Druid cluster. That's a manual process right now, but Imply just released the cluster API beta, and we'll be able to automate that and integrate that with our CI pipeline. So I want to tell you about backfilling data, because this unique features to WhyLabs, if you compare us to the broader APM space, is that we allow backfilling historical data to use in monitoring. So imagine you're in the retail space and Black Friday comes around and all of your numbers are going haywire because you're getting lots of sales. Is that an anomaly? Well, if you compared it to the trailing month of data, it's a huge anomaly, and we would be sending people alerts, and that's not really what people want. Most people in the retail space would say, you should probably compare Black Friday this year to Black Friday last year. And the only way for us to do that is to enable them to backfill older historical data sets. So while we have streaming ingestion into Druid, we have about a 7-day window where we allow data to be streamed into Druid. However, when people need to backfill, months to years worth of data, all of that data lands into S3, and we're ingesting it using the parallel native index task. Now, a lot of the things I like about how Druid does streaming ingestion, it carries over to the parallel native index task. I want my ingestion. I tell it how many CPU cores, but most importantly, it's provision capacity that's separate from the rest of my cluster. So no matter if somebody said, "Hey, I want to upload 100 million data points," I would say no problem, because the Kinesis ingestion that's doing all of our streaming is totally unaffected. The queries are unaffected. The parallel native index task can ingest data from S3 at its maximum efficiency without putting any stress on other parts of the system. So it's actually safe to do large backfills during work hours. If somebody said, "Hey, we need to ingest 100 million data points into Elasticsearch," I would say, "All right, well, let's figure out which evening we can do that. That's so that we're not going to be impacting our customer." Huge win just operationally for us. So I think a lot of people pair data lakes with Druid. For us, gives us a way to do faster feature rollout. If we were a streaming only architecture, then let's say we ship a new type of calculation and we start writing it from this day going forward, and that's great. But a lot of the algorithms in the forecasting space need potentially months of data before they're doing anything actually useful. And what we don't want to do is create a new calculation and then have to have it feature flagged off for 2 months while we're building up enough data to actually turn it on and do some forecasting. So what we have instead is streaming data does stream data into Druid, but we also stream into the S3 data lake. And then periodically we have parallel native index tasks backfill potentially years of customer data into Druid. So when we create a new calculation, we can ship the new calculation, backfill it the next day, and then customers can be using it the same week. We can really shorten how fast we can roll out a new product feature. So a couple quick notes on parallel index tasks. Early on, disk I/O was a bottleneck, so pay attention to your disk I/O throughput. Also, individual tasks have about 30 to 60 seconds to spin up overhead, so you want to have fewer tasks with much larger indexing payloads than the other way around. So I want to talk about some of the challenges that we've faced. So we we have found that we need to have certain guardrails in place. Uh, it's really easy to write a Druid query that produces a multi-megabyte result payload. We've seen payloads large enough that they break JSON parsers or produce so many data points that it's too many for Chrome to render. And here's a super easy way to do exactly that. We'll have a query with an interval that goes from 2020 to 2021 with a second granularity. If you have the data points, that's 31 million buckets that squeeze into a JSON payload. And so what we find ourselves doing is we have guardrails on our microservice that as you expand the size of the interval that you're querying, we assert that they have a reasonable granularity that they're querying it, that they're rolling it up to. Same problem, but slightly different flavor is high cardinality group bys. In this case, if we do a group by on an event ID is a high cardinality key, then we can produce a lot of different buckets in a query response, and we need to protect against that too. So uh, I, I think having a microservice with those guardrails makes a lot of sense. Um, Another challenge that we have is that we use GraphQL, but we find more and more that it's a bit of an impedance mismatch for Druid. I think GraphQL is a better fit, more in the OLTP space. And I get the selling point of inverting control to the front end to try to build some of the queries. But when you get to the GraphQL backend and you're interacting with Druid, we lose a lot of the context that we need to write more efficient queries. Like, can we use a Druid top end query, which is way more efficient than a group by? Well, we might not have that context by the time it gets to us. Also, GraphQL makes it very easy to do small query fan out, even by accident. With Druid, given that your query is going to always be a scan with filter, it's better to have fewer scans and have a disjunction of filters than to have multiple small queries for each one of those filters. It just means less scanning happening overall. And GraphQL makes it really easy to do small query fan out, and it's also, we're also finding, I think that you can get away with that a little bit easier in the OLTP space, but I think the OLAP space is a little bit less forgiving. So my suggestion, if anybody's considering GraphQL, I would probably stick with REST. All right, that's it. If anything I was talking about with WhyLabs struck a chord with somebody, check out the project on GitHub. We also have a community Slack channel. A lot of WhyLabs employees hang out there, and they're all super friendly. And if anybody wants some WhyLabs swag, just hit this forum, and we're happy to shoot some out to you. So at that point, I'll open things up to questions.
Everybody, Charles here. If you have questions for Drew, you can put them in the Q&A or the chat, and I'll read them out. Ben just wanted to give you some props in the chat, saying that it was an awesome talk and really interesting details, and I definitely agree with him.
Well, thank you.
Cole has a question asking if you make your Druid enhancements, and I'm thinking he's meaning extensions, available publicly, maybe through the open source or whatever.
Right. So we are huge open source contributors on the WhyLabs project, and you can use that to profile in many different contexts outside of Druid. Actually, taking those statistical profiles and ingesting them into Druid is part of the secret sauce of the WhyLabs platform. So we haven't open sourcing those yet. But everything that we do as far as data collection and collecting statistical profiles is open source in the WhyLabs GitHub repo.
We have one from Jian. What kind of anomaly detection do you use on Druid?
Yeah, we're actually in the process of rolling out ARIMA-based anomaly detection, but that's just the tip of the iceberg. I think that we'll be expanding on that very rapidly as part of our product roadmap.
More questions? Mikhailio was talking about how he loved the comparison to Elastic too. I thought that was really effective, going through the use cases. That was really good.
Thanks. Yeah, and I feel like I was picking on Elasticsearch a lot, but really that applies to a lot of the data tiers out there. Misusing OLTP data tiers tend to have a lot of common pain points.
Karthik was asking if you considered any other OLAP platforms other than Druid, and what difference did you notice? He missed I don't think we talked about that. He was apologizing in case you had touched on it before.
I had not. I think the closest runner-up for us was going to be ClickHouse, but ClickHouse is written in C, and once we realized pretty early on that we're going to be in the business of extending our data tier with new algorithms, and most of that happens in Java Python. So we ended up kind of narrowing our search down to pure JVM-based solutions.
Yeah, that's a pretty good differentiator.
Yeah. Yeah, it's also nice that there's a lot of Druid extensions already publicly available and many different flavors of them. And so just about everything that we will probably ever want to do, there's already some really good prior art that we can start with. I wouldn't want to have to write an extension, with a blank sheet of paper.
More questions for Drew? If not, maybe we'll go ahead and wrap it up. Thank you so much, Drew, for that fantastic presentation. It was very interesting and insightful.